the bigger the project, the open source project, probably the more CVEs you might have. And Christoph is going to explain us how he's triaging CVEs for the Linux kernel.
Yeah, hi everyone. My name is Christoph Steiger. I work at the Linux Expert Center at Siemens, and I'm going to talk today about triaging CVEs for the Linux kernel. Unfortunately, I only got a lightning talk. I would have loved to talk a lot more about this. I'm going to focus today on explaining what the problem with CVEs in the Linux kernel, and why if you have like a product based on Linux, you need a solution, and we built something that might be useful for you. I said we, so we is in this case not only Siemens but also the Civil Infrastructure Platform, CIP, which is a project under the umbrella of the Linux Foundation, which offers kernels and real-time kernels for industrial and infrastructure applications. What it provides is super long-term support kernels, which live a lot more longer supported than normal kernels, which is usually 2 years. And in CIP, the kernels are supported for up to 10 years. This is like, I would say, one of the big success stories for Siemens with open source, because we are very involved in this project. This is an open source project that is used in a lot of Siemens product, and we have one of the maintainers here, Jan, sitting in the crowd. And yeah, so the project we developed is now part of the CIP project. Why do we do anything? Why do we need to do anything? CVEs are, a common thing in software development. We need to deal with them in every software we distribute. Vulnerability remediation is nothing special, but the kernel has a lot of CVEs. The 4.19 Linux kernel version, which had its end of life, I think December last year, had an email from one of the maintainers there, which said that there's currently more than 1,000 unfixed CVEs for this end of life product. This is a lot. If you ask the Linux kernel, what do we do about these thousands of CVEs for this now end-of-life kernel, the kernel team will tell you, well, just update to the newest kernel, which, as most of us know, is, especially at Siemens, not something which we can easily do, especially if you support it for a very long time. The version jumps you have to do is too big. It's not possible. And we can already imagine that in 2 years, when the CRA comes into force, some regulatory officer is going to come to us, say, you use this old kernel here. I know there's 1,500 CVEs. What did you do about them? And if you do not have a good response there, you're going to be in trouble. Now, to understand why there's 1,000 CVEs, and this is not actually a problem, we need to understand how CVEs in the kernel are handled. You could talk an hour about this. There's a very difficult history for the kernel and the CVE. To summarize, CVEs are slapped onto the kernel without their consent, probably. And yeah, you can see it's probably not readable, but the important thing is that CVEs are just a mail you get after something has been fixed in the kernel. So there's nobody looking around in the kernel source code looking for bugs and then telling the kernel security teams, hey, we have a bug there, and then a CVE gets fired, then a fix happens. It's the other way around the Linux kernel. Somebody fixes a bug. The bug then finds its way into mainline. Then the kernel CVE team looks at the bug, says, hey, this looks relevant for security. Then a CVE gets released which says, hey, the CVEs have been fixed. Right? So it's the other way around. First the fix comes, then the CVE is applied to that. There's around 60 CVEs each week, which explains the thousands of CVEs we have at the 4.19 end-of-life kernel. And to understand why there's so many CVEs, we need to look at how the Linux kernel is used. Because the Linux kernel is huge, and the Linux kernel doesn't know how you actually use your kernel, right? Your Android devices, an embedded IoT device, your laptop, it's going to be a completely different use case. They're going to have widely different kernel versions, and the kernel doesn't know and doesn't even want to know how you use your Linux. And a good example to give is what is security relevant for the CVE kernel team. There's a configuration option in the kernel which is called panic on warn, which does exactly what it says. When the kernel emits a warning, it panics, so it crashes. This is useful for some cloud deployments where you don't want to, like, whenever you feel that the system is like struggling with something, you get a warning, you just want to like save all the data, restart. Okay? But what does that mean for security? If you somehow find a way from user space over the network, whatever, to cause a warning in the kernel, with this configuration option, the kernel crashes, which is a denial of service attack for someone. So suddenly, whenever you can emit a warning from user space, for example, over the malformed network package, it is a CVE. That's where the 60 come from. Now, if we have a product based on the Linux kernel, and we want to deal with 60 CVEs each week, we need to look at our use case. We need to know it. I already said the Linux kernel is huge in numbers, 85,000 files, 40 million lines of code. That was like 610, it's probably more now. For a typical use case, only 5 to 10% of the Linux kernel are actually used. Right? So like 10% is probably your smartphones, 5% and even less is like embedded IoT devices if you strip down the configuration enough. This means that if you assume, for example, that all the CVEs are evenly like distributed along with all the files in the kernel, we don't need to care about 60 CVEs, probably around 3 a week, which is a lot more handleable, but still much. Okay? But what this also means is the Linux kernel team, the CIP team, is not able to do this CVE remediation, this filtering of CVEs for you. You have to do it yourself. You have, like, the kernel team or CIP can provide tooling that helps you actually figure out which of the CVEs are relevant for you, but if you are the only one who knows your use case. So you need to be, you are the one who needs to do the actual checking. And this is the kind of tooling that we developed, and I'm gonna quickly explain what our goals were and then show you how it looks like. As I said, we have to provide tooling that each product user that has a Linux kernel needs to have in their build somehow. And so we need a kernel version. We have to somehow specify the use case. I'm going to come to that, how we do it right now, and a CVE. And then we have to like give a verdict. This is relevant or this is not relevant. It's a CVE. And we need to be fast because for a product, you have multiple products, you might have multiple releases flying around somewhere, so multiple kernel versions, very, very likely. You have 60 CVEs a week. CVEs get updated, right? They're not like a stable thing. And so you can expect to run this tool for probably 100 CVEs each week for each kernel you're flying around somewhere. Okay, so we cannot build like the whole kernel every time we check a CVE or something. No, it needs to be quick. We have to make sure there's no false negatives in our verdicts, right? Otherwise, a security vulnerability slips through, we get cybered, everybody's angry. And what is like a plus we also want to provide is useful information to actually like make it easier to resolve a vulnerability. And this should also, like the whole output should also be in a standard format because again, this is something that the general public will use, like, and it needs to have a format that everybody can easily use. Okay, the use case, I talked a lot about it. We actually used kconfig, right? So it's like the set of configuration options you actually use to configure your kernel because this is like the best machine-readable format we have to describe a use case. And it also has like the big advantage that from the kconfig options, we can directly go to the source files, which are also available in the CVE, and then we can start to like do some magic and figure out if files are built and stuff, and actually see if this CVE is built by us. So we run a number of checks. Each check gives a verdict, says this is relevant for us, this is not relevant for us, this specific CVE we check. Each of these checks is conservative in its assessment. That means if we encounter something we don't like, we are unsure, or like just something strange happened, we raise our hands and say, okay, whatever, the CVE is probably relevant for us because we've failed in our analysis. These checks include simple commit checks, right? There's, as I said, the Linux kernel like first does the fix, then the CVE. In the CVE, there's often like an introducing, like where the bug was introduced, commit included as well. You can just start looking around. Is the fix somewhere in my tree? Is the introducing commit somewhere in my tree? There's also like descriptions in the CVE that might help you to ignore certain ones. Some get rejected, some get called back later on. You can figure that out from the CVEs themselves. And then there's more sophisticated checks which actually start looking which parts of the kernel are built based on your configuration, and then looks into the CVEs, sees which parts of the kernel are affected by the CVE, and tries to figure out if the CVE actually affects parts of the kernel you are building. Okay, how does it look? I'm not sure. You can read it somewhat, maybe. You can see on the left side outputs of this tool. It's in JSON. This is proprietary, of course. You can see the checks that were run. First, we checked introducing commits, ignores in the CVE message, and we can see we found the introducing commit in our history, which is bad. So it's irrelevant. And then we started checking the files that were mentioned in the commits, and we can see, okay, we needed some specific configuration options enabled, which we do not have in our kernel, which means we can actually exclude the CVE. This is not relevant for us because we are not having the configuration options enabled for the bug that is described in the CVE. We have it in the standard VEX format, which you can attach to your SBOMs or otherwise consume. Yeah. Now, the more interesting part is now, this is like one check that runs. If you actually run this tooling for the CIP kernels, which is, I think there's 5 kernels now in the supported super long-term stable support for the CIP project, which is 4.4, 4.19, 5.10, no, 6.1, 6.12. And I ran all of these kernels. It took all the CVEs from the year 2024, which is like 7,000 or something, used a CIP dev config, which is a configuration which all the members of the CIP projects, they put in their use case, they describe what they need. It gets merged into one big configuration. And with that, I could exclude 90 to 90% of the CVEs. The range here is because the older the kernel is, the less we can exclude. So 90% is like the lower bound here. That would, like, all of these could be excluded. That would mean, like, in weekly numbers, if you use this tooling, you would, in the worst case, have to review 6 CVEs for each of your products. Right? This is still a lot, but much more handleable than 16. I mentioned about 1,000 CVEs that were mentioned in the 4.19 EOL message. These are pre-filtered, of course. The Linux kernel looked at the ones which were unfixed and are actually probably inside the 4.19 kernel. And even there, with this tooling, we can, from these 1,000, can exclude 56%. Now, of course, this should be improved because 6 a week is still very much for each of your products. The problem is that with the approaches we used here, it is very likely not possible because we need a better way to describe our use case. Because security is also a threat model, right? If you have an embedded device that is completely in a secure network, you don't need to care about network vulnerabilities, right? If you don't have a shell, you don't need to worry about privilege escalations because nobody can actually access the shell. It's not possible in the tooling yet to provide this kind of information, but if we could actually get this information somehow in the tool and also have similar information in the CVEs to actually match it, it would be possible to probably exclude even more. But yeah, this is an area of improvement. I think now it's good enough to show here, but we can always do better. So please contact us. If you have a Linux kernel and you don't know how to deal with the CVEs, we have tooling which you can find under the kernel CVE Triage repository here. We should work together. You have to do it by yourself. We have some tooling here. If you have a use case that is not like covered by this, I think we should all work together, because otherwise every Linux kernel in Siemens or out there is going to have the same problem, is going to solve it. We're going to have 1,000 solutions. Thank you. We have 15 seconds for questions.
Thank you for the introduction. I believe we will try to adopt the mechanism at CCP team as soon as possible. But I have one question. I wonder, how do you come from the config to the list of the files, to the set of the files affected? Do you build the kernel fully, or do you try to pretend that you parse the build make files correctly? Because the final configuration would depend actually on the target tool chain.
Yeah, we do not build the kernel because like that would be too slow. We use tooling which is called Kmax, which more or less builds a graph from like the whole kconfig space, and we can query it to ask which files are actually built for which configuration options. Yeah, I mean, we rely on this tool to be correct, but yeah, if there's problems, like maybe we should talk. But yeah, we don't build the kernel. Okay.
Good. Thank you very much, Christoph.
Thank you.